All right, so here is where the elbow joint is. That's the point of application. And this is the rotation axis. So in between the rotation axis and the point of application, that's the 27.5 centimeter radius, along with the in between the rotation axis and where the muscle actually attaches to the humerus, the actual bone, I didn't draw it in, is 12 centimeters. And that's the shoulder right here. This is the deltoid muscle. And this is the 15-degree angle in which it will make. So here is the force of gravity wanting to pull the body down, the arm down, and this is the force with which the deltoid muscle is trying to pull up, a fighting gravity, and that's what makes the 15-degree angle. And neither of these forces are parallel, okay? They are both perpendicular to this line right here. In between the rotation axis and point of application, both of these forces are perpendicular. So not only that, but also it's in equilibrium, okay? There is no movement, okay? So this is equilibrium. So we can say that the force and the torque are both zero. Okay, so we can set it both equal to 0 because of that. And also this is the equation with which I'm going to use, okay, to find the torque. Okay, because I'm going to need to find the torque of the point of application before I can find the force generated by the deltoid muscle. So the first part is straightforward. We know what the force of the arm is. It's 30 newtons. And we know what the radius is of the arm between that rotation axis and point of application. It's 0.275 meters. I just converted it. And the torque of the arm, or at least between the point of application and rotation axis, is 8.25. And also noting this, okay, so that's the torque due to gravity. Okay, so that's the torque due to gravity, and it is going to be clockwise. So that means it's going to be a negative torque. Okay, because it's pulling it this way, which would be clockwise. All right, so that's going to be negative, and that's going to factor in later. Okay, now since we have that, we need to find the torque. Now we need to find the torque exerted by the deltoid muscle. Okay. Now, again, this force is perpendicular, but we don't know what the force is, so it's just sine of 15 degrees. Okay, because it's opposite that angle. All right. So that's sine of 15 degrees, but we do know the radius, and it is 0.12 meters. Okay, from the rotation axis to where that muscle is actually going to connect to the bone, the humerus right here, which I didn't draw. So that's 0.12, okay? So that's what we know for the torque of this, okay? But now I can substitute this in to try to find the force, all right? So it's the force multiplied by sine of 15, multiplied by 0.12 meters, subtracted from the previous torque due to gravity. Okay, and that's minus 8.25. Now we can set this equal to 0. It's in equilibrium. Okay, so now just rearranging it where 8.25 is on the other side because we want force. That's how it's going to end up looking. And the force due to the shoulder, the deltoid muscle, is 265 newtons.